Good morning, students. We are in fourth unit. Present, our topic is Principles of Geophysical Study by Seismic Methods and Seismic Refraction Methods. So, guys, in this class, we are going to discuss what is seismic method and what is the principle involved in that, and what is the use of seismic methods and seismic refraction methods, vastly in which sector we have to use these things. These all things we will discuss in our class. Guys, seismic method, guys, measurement of seismic wave travel time is one of the most common geophysical method. Seismic exploration is divided into refraction and reflection surveys, depending on whether the predominant portion of the seismic waves travel is horizontal or vertical. Refraction seismic surveys are used in engineering geophysics and petroleum exploration. Seismic reflection surveys, on the other hand, detect the boundaries between different kinds of rocks. This detection assists in the mapping of geological structures. Seismic energy is detected on land by using devices called geophones, which treat to on-site ground motions. Guys, here the seismic survey objectives, preparation and planning, parameter selections and instruments and field operations we are going to discuss broadly. So objectives, regional exploratory investigations. The in regional exploration investigations, we are using seismic methods for delineation of structure and stratigraphic anomalies. Here, guys, delineation means drawing. Just we have to understand as a drawing. Delineation is nothing but a drawing of structural and stratigraphic anomalies. Here, in petroleum exploration, these structural and stratigraphic are the most important, because always oil and gas occurrences in the only anticline structures and field development to mark suitable locations for field development and for reservoir studies. Prospect delineation to mark the depth of prospective horizon and trap closures. And guys, preparation here, available budget and time and available data. Available data means geological data, geophysical data, and other information we need to preparation for oil and gas explorations. And planning and designing. Acquisition parameters, minimum offset and maximum offset, source interval, receiver interval, number of channels, and source. It means dynamite vibrations. So bit invitation. And guys, here receiver and source parameter selection, planning and designing, guys. Here receiver and the source parameter selection, spread type, receiver layout, and source type. So guys, instrument for seismic survey, geophones. We are using five types of the instruments: geophones, seismic cable, seismograph, energy source, and seismic group. And the source type, source type, dynamite, vibrosis, hammer, and weight drop. Dynamite. Parameters, for example, SP interval, hole depth, and the charge size. Here, short hole depth, charge size, short point interval, and number of holes, source array pattern. And here, guys, during a field work, the drilling of the holes is often the slowest field operation and grow when all the acquisition work. This is the image indicates that. The blast of explosives produces a very strong energy, placing of the explosives to the bottom of a hole from 1 to 35 meters, and the energy is better distributed. In order to make the holes, a hammer perforator, an auger or drilling rig is used in the sand. A simple metallic tube is very efficient. In some desert regions where the drilling is impossible, explosives can be suspended and exploded in the air about 1.5 meters from the ground. This method very noisy and dangerous. Yes, and uh, vibrosis. This is called the vibratory sources. Vibratory sources, guys. This is the vibratory sources images and a hammer. This source constitutes in many cases the best energy source for shallow seismic with a large frequency spectrum and a good energy. But the environment must not be too noisy. And weight drop systems and field procedure, guys. Mm, planting geophone along a straight line and detonating, generating seismic waves by detonating explosives on one end of a line, recording seismograph, picking first arrivals, plotting of data to determine V1, V2, and H1. Survey crew. GPS used by the survey crew for locating the source and receiver points of the seismic lines carried on their shoulders. It is connected with two external batteries and a receiver which receives the single signal from the satellite, and short points and receiver points. Source points with red paint, receiver points with white paint. After locating the points, the crew mark the places of source and the receiver points, finally marking a seismic line. And drilling crew. The drilling crew uses jackhammers for shallow holes, man portable drilling rig. For deep holes, man portable drilling rigs are used. Loading crew. After drilling short holes, dynamite is loaded in them using dynamite sticks. Here, detonators are placed in the dynamite stick used to initiate the blasting of dynamite, and lowering of charge in a drill hole with detonator in them. Hole is loaded and filled with sand. Loading is done and place is marked. Layout crew. Here, this crew first of all lay out the geophones on the seismic lines as spread. These geophones are connected to each other by the takeout cable. And cable and geophone. This is the geophone string. This is the link cable. And the layout from front crew. This is the cable layout. Geophones plantation. Rod crossing and line. Then this is the source. This is the receiver. So guys, takeout cable is then connected to station unit box. Here the station unit box, all the station unit box is further connected with one crossing station unit box of an array. The yellow cable called jumper cable is finally connected to recording truck through which all the information goes onto it. Recorder cable plug in the recording truck. Monitor on which the observer control all the activities on a seismic line. The recorder which records all the data coming through cables. The recorder which records all the data coming through cables. The tape driver records all the data on the magnetic tapes or cartridges. The thermal plotter used to make a hard copy of the recorded data. Device which synchronizes the blaster before shooting recorder presses arm button to charge the detonators. At the same time, the blaster operator presses the arm button in the blaster. The recorder presses duo button to blast the dynamite. Seismograph, portable recording system, shooting crew. A bag carried by the shooting crew is called the blaster. It works in coordination with the seismic source synchronizer, blast view and seismic line. Here guys, a seismograph, a recorded result of short point after the blast. Seismograph, a recorded result of short point after the blast. End of survey. After all the shots are recorded, everything is wounded. The data is sent to the operator company. Then operator company sends data to DZPC. The place is restored by the green team and inspected by the client company. And seismic recorder. Seismic recorder picks seismic signals or vibrations from geophone sensors and records them on magnetic media in a digital format. A seismic recorder consists of multiple channels, each connected to a geophone group. It is similar to an audio tape recorder, which picks audio signals from microphone and records them on a magnetic tape. Guys, seismic recorder main modules. Uh, Free amplifier, filters, low cut, notch, and a high cut anti-lies, amplifier, multiplexer, analog to digital converter ADC, formatter, tap or cartridge, or DVD writer. So guys, seismic recorder black diagram suppresses ground roll, remove power lines induction, avoid anti-liasing. So geophone, free amplifier, low cut filter, nudge filter, high cut filter, antennas, amplifier, multiplexer, analog to digital converter, formatter, writer, or tape. This is the suppress ground rule 10 Hz. Remove power lines induction 50.6. Here avoid anti-liasing one. So geophone. A geophone is a transducer which transforms mechanical energy seismic vibration into electrical energy. It consists of a moving coil and stationary magnet. The movement of the coil due to vibration creates electromagnetic flux proportional to the magnitude of vibration. So guys, this is the vertical and horizontal geophones used in seismic surveying. Geophones consist of a bar magnet fixed to the container and a surrounding coil suspended by springs. Vertically suspended systems are sensitivity to vertical ground motion, and horizontally suspended systems are sensitive to horizontal component of ground motion in the direction of the coil axis. So this is the input from geophones or a capacitor or output from the filter. So filter output amplitude, filter output amplitude, and amplitude frequency. This is the input from geophones. This is the Hing pass filter, band pass filter. Electronic circuits for a low pass or high pass and band pass filtering of alternating electric signals. Seismic wave motions are transformed into electric signals by receivers, that is geophones or hydrophones. These electric signals can be filtered by the electronic filters to reduce or eliminate certain frequencies. A filter that removes some higher frequencies is called a high cut or low pass filter. Similarly, filters can be designed to pass higher frequencies or only a band of frequencies. The band of frequencies that is removed is called band rejecting filtering. Spread geometry. The most common recording type consists to send seismic waves from one short point and to record reflected waves with many or more. Geophones regularly disposed on the ground along a seismic cable. The CDP is the reflection point in depth. The CMP is the midpoint on the ground between shot and a geophone. With a switch, roll along switch, the observer can displace the recording geophones along the line with a constant number of active geophones 24, 48 or more. The aim of this process is to add the travel having a reflective common point in order to improve the signal noise ratio. With 48 active geophones, there are 24 travels adding a common reflector. So this is the basic spreads. Conventional spreads were seismic reflection. This is the diagram portion of the shooting. Short recording geophones, short recording geophones, short recording geophones. The shot or the vibration point can be situated at the extremity of the activity geophones and shot at the center of geophones so split spread shot at a certain distance offset of first geophone. The last geometry allows to have a long distance of offset. The second is more adapted if the reflectors are tilted. And a short or split spread, head waves, reflected waves, reflections, air wave, ground roll, and short loss, short point and distances. Diagram of the CDP acquisition. Common depth point, layer 1, velocity 1, and layer 2, velocity 2. So this is the geophones, layer 1 and layer 2. Seismic ray line in CDP acquisition. Examples of seismic records, record 1 from record 2. This is also record 3, record 4, record 5, record 6. This is the apparent path V2, V1, and H is equal to S1 IC, and the ray path. This is the X refracted wave. Distance between geophones, minimum depth and maximum depth. So distance between geophones 50, 1 meter, 2 meter, 5, 10, 50. Minimum depth 10, 20, 50, 100, and 250. 10, 20. And 100, 500, 1000, maximum depth 5000 meters. So signals and noise. Any events of the interest are called signals, while rest are called noise. Signals or noise are relative terms, as in a certain set of analysis, an event may be considered as a signal, while in another analysis it is considered as noise. If seismic acquisition and processing, our major emphasis is to enhance the signals and suppresses the noise, thus increase the signal to noise ratio. Noise. Noise is the information on the seismic record which one does not wish to use. Types of noise. Random noise or incoherent noise or coherent noise. So random noise or incoherent noise. It is the seismic energy that does not align up from trace to trace or record to record on seismic record. It displays no systematic pattern. These noises is uncorrectable. We can overcome random noises by recording more than one traces from the same location. Sources of random noise. Wind noise, water flow noise, small movement within the earth, local noise, and bad geophone noise, and other coherent noise. It is seismic energy which aligns from trace to trace or record to record on seismic record. Often it is very similar to the single and usually more difficult to overcome than the incoherent or random noise. By examining the patterns of coherent noise, we can devise procedures to reduce it. Source size and source depth, electric filtering, receiver arrays, source arrays, deconvolution and editing and muting. Sources of coherent noise, multiple reflections, direct arrivals and refracted waves, diffraction events, and ground roll. This is the guys source and the simple multiples. interbed multiples. Here, ghost reflection are direct downgoing pulses. Direct and refracted waves. Head waves are always the first event seen on a record. They are linear and often very visible and strong. Sometimes they can disappear with a large offset. Many geophysicists try to remove head wave using a surgical mute. Head waves are always the first event seen on a record. They are linear and often very visible and strong. Sometimes they can disappear with large offset. Many geophysics try to remove head wave using surgical FK filtering, adopted NMO stage mute value. But in some cases, uppermost reflection or refraction can be very close and difficult to distinguish. Refracted wave. In seismic reflected survey, the refracted events comes on first arrival. Ground rolls are raylet waves which appear as second arrival and seismic reflection. Surface wave really low, primarily low velocity, low frequency signal with relatively higher amplitude seen below shores. They override the useful reflections. They can be reduced using frequency filtering and FK filtering. So diffracted events. This is the diffracted waves, guys. As fault and some unconformities, diffracted waves are generated on seismic section. So refraction 1, refraction 2, reflection, air waves or ground roll. Refracted waves, primary reflection, multiple some reflections, aerial noise or air wave, wave of surface, parasitic noises, and S waves. The seismic reflection takes an interest essentially to the P-compression waves in the setting of seismic studies for the geotechnical. The recording of the S waves can to provide how to be useful for the sharing modulus calculation. In knowing the velocity of the P waves and S, it is possible of calculating the Poisson's ratio. Advantages and disadvantages. The refraction methods. Advantages. Refraction observations generally employ fewer sources and receiver locations and are thus relatively cheap to acquire. Little processing is done on refraction observations with the exception of filtering to help in the process of picking the arrival times of the initial ground motion. Because such a small portion of the recorded ground motion is used developing models and interpretations is no more difficult than our previous efforts with other geophysical surveys. Disadvantages. Refraction. Seismic observations require relatively large source receiver offsets, distances between the source and where the ground motion is recorded the receiver. Refraction seismic only works if the speed at which motions propagate through the earth increases with depth. Refraction seismic observations are generally interpreted in terms of layers. These layers can have deep and topography. Refraction seismic observations only use the arrival time of the initial ground motion at different distances from the source. A model for the subsurface is constructed by attempting to reproduce the observed arrival times. So refraction survey advantages. Amplitude of refraction are large, best for exploration of shallow structures, easy to process and interpret. Disadvantages. Exploration for deeper structures is difficult because of large excrude distances, blind to low velocity layers, and reflection seismic observations are collected on small source receiver offsets. Reflection of seismic methods can work no matter, excuse me guys, maybe this is the, no, not repeated guys. So this is the another slide. So reflection seismic methods can work no matter how the speed at which motions propagate through the earth varies with depth. Reflection seismic observations can be more readily interpreted in terms of complex geology. Reflection seismic observations use the entire reflected wave field, that is the time history of ground motion at different distances between the source and the receiver. The subsurface is directly imaged from the acquired observations. Disadvantages: because many source and receiver locations must be used to produce meaningful images of the Earth's subsurface. Reflection seismic observations can be expensive to acquire. Reflection seismic processing can be very computer intensive, requiring sophisticated computer hardware and a relatively high level of expertise. Thus, the processing of reflection seismic observation is relatively expensive. Because of the overwhelming amount of data collected, the possible complications imposed by the propagation of ground motion through a complex set, and the complications imposed by some of the necessary simplifications required by the data processing schemes. Interpretation of the reflection seismic observations require more sophistication and knowledge of the process. So, seismic reflection surveys. Advantages: geophone spread needed is relatively shorter, not blind to low velocity layers since acoustic impedance exists for every layer, convenient for deeper exploration. Difficulty in recognizing reflected waves, small amplitude, uh, obscured by overlapping reflected and surface waves. Guys, here I want to show a video that is helpful to
It's complicated, so let's start with the analogy of bands. Bands can't sing very well, so they send out little waves of sound that bounce off the objects and then come back. So it's called sonore. It's complicated, so let's start with geoscientists have a secret weapon called seismic exploration, and it involves sending acoustic energy, which takes the form of waves, into the ground and will send a picture beneath the surface. It's complicated, so let's start with the analogy of bands. Bands can't sing very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonore. It's what you might call the sound picture of their world. It's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound waves and listen to oil and gas deposits are in a particular area. Geophysical companies bring large trucks that have big vibrators on them. Each scientist generates the acoustic energy or vibration. They use geophones or sensitive seismic microphones to hear sounds. But sometimes they set off small varying charges. They send many geophones on the ground line, and they are attached to a recorder inside another truck. Vibrators send thousands of wavelets down to all the different layers of the earth. Some of the wavelets bounce off the boundaries between the rocks below the surface and are reflected back to the geophone when they are ready to. Each geophone along the cable sends the received wavelets to a recording truck and stored. How the wavelets reach into the subsurface of the ocean? That's offshore seismic, and it just requires a different device to send out the wavelets and record those that are reflected there. I would say a seismic recorder does it with a specially designed back end, so it's easier to link cameras or streamers. Streamers and microphones called hydrophones are attached to the electrode. Several of these strangers or global hyperloops. Acoustic sources are denied from the strangers and release compressed air, which creates the wavelets. These wavelets travel through the water, subsurface of the water, just like on land. They bounce off the rock layers and then return to the hydrophones to be recorded. Here's what seismic looks like after it's been recorded. Basically, it's a bunch of squiggles. There's still a few more steps to go before it begins to look like an actual picture of Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath, the data has to be processed. It takes a large supercomputer cluster to process the seismic data. These computers look for all traces made and filter out everything we don't need, such as vibrations made by a tractor in the field. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I didn't see any oil and gas there. Geoscientists can look at this process data through trained eyes and make an informed decision about whether gas deposits or the geologic structures. Seismic data leads to a high percentage of drilling success with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
Okay, guys, thank you for all of your patience. In next class, we will discuss next topic. Thank you.